Okay, so the recording is happening at this time. And again, I welcome you and hope that you're doing okay. So do you have any questions right now before we get started in some additional content from chapter 2? Okay, all right, not hearing anything, we'll get started. So at the end of last class, we started talking about chemical bonds and we had defined some ionic bonds, right? We had that example of sodium chloride and said that an ionic bond is an attraction created between atoms when one atom donates or shares one or more electrons, okay? And so we pretty much finished that example. So I will continue next talking to you about covalent bonds. Okay, so covalent bonds are highlighted on page 34 of your textbook, page 34. I'm going to share my window with you, my screen with you at this time. All right. Okay, so let's get back into it, folks. We're talking about covalent bonds. Let's see if I can get my technology to cooperate here a little bit. Okay. All right. Covalent bonds. So we've defined all the bonds in your last class section. You have the definition. A covalent bond is an attraction created between atoms that share electrons. And there's two major categories of covalent bonds that we need to talk about. There's actually two types. Okay. They are the polar variety of a covalent bond and the nonpolar variety of covalent bond. Okay. And so I'll talk about the nonpolar variety first. Okay. In the nonpolar variety of covalent bond, we have an equal, or you might say even sharing of electrons. Let me just put this in parentheses. There is an equal sharing of electrons. And so an example of that would be a typical carbon-carbon bond. Okay, that would be an example that I could give you. So carbon, carbon with a line through it. And remember the line that's, in between these bonds right now, the line is nothing more than a symbolic representation of the bond, right? The line is a symbolic representation of the bond. If you ask yourself, well, what is the bond? The bond is really the attractive force created by the motion of the electron. So that bond, that little squiggly line there, well, actually that straight line, is simply the motion of electrons around the nuclei of those two carbon atoms, okay? And so that's one of the things that makes this very hard to convey to you because, when you read your book or look at the notes in front of you, you're looking at a static image where there's nothing moving, there's nothing obviously in motion, but we need you to imagine that there are in fact electrons moving around these atoms, okay? And so the electrons in these electron shells, in the shells of figure 2.5 that you see here, right? You see electrons there, but they're kind of like stuck in mud. They're just sitting there. But in reality, in real life, they're actually moving. So if I could represent the nonpolar covalent bond for you a slightly different way, if I redraw this bond, okay, so I've got two atoms here, two carbon atoms, and I should have changed my color, but I didn't do that. At any rate, if I momentarily represent the electrons that are in motion, go ahead and watch your screen very carefully, okay? What I'm trying to suggest to you is that the electrons that are being shared are kind of moving like this. Here we go. Now, I'm not a very good artist, but what I'm hoping you see is that roughly the volume of the dotted line around the left atom is roughly equal to the volume of the dotted line around the right atom. And so what I'm trying to tell you is that when you have an equal, right, an equal sharing of electrons, that means the electrons are moving in such a way that the electrons being shared spend around about 50% of their time around the left atom and another 50% of their time around the right atom. Okay, so the 50% on your screen represents the amount of time that the electrons being shared spend around the nucleus of both the left and right atoms. And you can say they are equal, they're even. Okay, so this kind of scenario creates a nonpolar covalent bond. And you can think of this as a tug of war. Now, if we think about a tug of war, I'm sure you've all seen a tug of war. If you haven't participated one, maybe a field day at high school or something like that. Think about a tug of war, right? You've got a rope, you've got a flag that hangs down from the middle of the rope, and you have two teams, and they're both pulling in opposite directions to try to pull the flag towards their side. Well, imagine if that tug of war was in fact between two teams that are identical. Imagine if you had a tug of war with a clone of yourself, you versus you. You can imagine if it was you versus you, that you would be pretty equally matched, right? So that is what we're talking about here. And do you notice when we drew this, that in this scenario, the nonpolar covalent bond was in fact between atoms that are the same type. Notice both atoms are the same. And so that goes a long way to predicting whether a bond is going to be polar or nonpolar. If the bond is between two atoms that are exactly the same, a carbon and a carbon, a nitrogen and a nitrogen, a hydrogen and a hydrogen. If we're talking about two atoms that are the same, almost always, there are some nuances, but almost always you're going to have a nonpolar covalent bond circumstance. Okay? Gang, do you have questions about that? Anything you'd like to ask? Okay, let's continue. On the polar side of things, so the left side of our screen here, on the polar side of things, you can have bonds that are covalent due to an unequal sharing of electrons. Okay, unequal. And so in this scenario, the example that I could give you would be a hydrogen-oxygen bond. That's a pretty good example of a polar covalent bond. Okay. And so, you know, the HO bond that I've drawn to you is a typical representation. If I redraw these atoms and try to represent the motion of the electrons like it did last time, okay, then it would look kind of like this. Here we go. Notice how that figure 8 is very lopsided, so that the volume of space around the hydrogen atom is very small compared to the volume of space around the oxygen atom, which is significantly larger. So in this scenario, we might have a situation where the electrons are spending 10% of their time around the hydrogen atom, and they're spending 90% of their time around the oxygen atom. Okay, And obviously in the polar covalent bond, you notice that the atoms are different. Okay. So as a rough approximation, you can predict whether a bond is going to be polar or nonpolar simply by looking at the identity of the atoms on both sides of the bond. Now we can do something even more that would allow you to reason your way to predict whether a bond would in fact be polar or nonpolar, and has to do with reasoning with something that you're already aware of, that we've already talked about in chapter 2 of our book. Okay, so I'm going to ask you to stay with me on this, and let's see if I can find somebody to ask a question of here this morning. Okay, one moment. All right, so if you have your textbook open, please, you can keep your page on page 34, maybe put a pencil in there or something, but then go back to page 31, figure 2.2, figure 2.2, page 31, figure 2.2. Okay, so I'm going to ask someone a question, and please just unmute your microphone and say hi to us. Okay, so I'm going to ask Emmanuel. Emmanuel, can you hear me?
Yes.
Okay, good morning, Emmanuel. Okay, so Emmanuel, I have a question for you. Emmanuel, first off, do you have your textbook in front of you?
Yes.
Okay, so on figure 2.2, Emmanuel, please tell us all, from looking at figure 2.2, how many protons are in the nucleus of a hydrogen atom?
Can you repeat your question?
Okay, Emmanuel, how many protons are in the nucleus of a hydrogen atom? You should be able to figure that out by looking at figure 2.2.
1.
Okay, very good. So stay with me, Emmanuel. So we have 1 proton. Okay, I'm going to draw a +1 there on the screen. So Emmanuel, how many protons are in the nucleus of an oxygen atom?
8.
8. Okay, thank you, Emmanuel. You did great. So Emmanuel, let me ask you this. If we imagine, excuse me, if we imagine that there's a tug of war for electrons between team hydrogen and team oxygen, if team hydrogen has 1 positively charged proton and team oxygen has 8 positively charged protons, doesn't it make a lot of sense that oxygen should be more capable of drawing negatively charged electrons towards itself? Does that make sense, Emmanuel?
Yes.
Okay, all right. Thank you, Emmanuel, for your participation today. I really appreciate that. So again, folks, think of a tug of war. We've got team oxygen with 8 team members, 8 protons. We got team hydrogen with 1 team member, 1 proton. Team oxygen is just going to be a lot better at drawing electrons towards itself, which is why down here we're drawing it as 90% of the time oxygen is using the shared electrons versus 10% of the time team hydrogen is using the shared electrons. Okay. So, if you ask yourself, well, which is the stronger bond? For a variety of reasons that we won't dip our toes into just right now, the nonpolar covalent bond is going to be stronger than the polar covalent bond, right? Nonpolar is going to be stronger because of the equal sharing of electrons. Folks, do you have any questions right now? Okay, so in your study time, there's something that's going to come up in your study time that I want you to pay attention to because I might ask it on a future exam. I want you to pay attention to a concept called electronegativity, and I'm going to just highlight it here at the bottom. Okay, be sure you study electronegativity. Okay, be sure you study that. Okay, I'm just taking a quick look here. Electronegativity is a boldface word on the left side column of text on page 35. Okay, be sure that you have a working understanding of what electronegativity is and see if you can incorporate your knowledge of electronegativity into your understanding of chemical bonds. Okay, any questions before we continue? Wish my document would do what I want it to do. Okay. All right, here I go. I want to keep on going here. All right.
Please, what page is electronegativity?
Okay, electronegativity on the current edition of the textbook is page 35. Okay. Anything else? All right, let's switch gears, and we're going to now go to the topic of hydrogen bonds. Okay, so we've covered 2 of the 3 bonds, and now we're going to tackle the third one, which is hydrogen bond. Okay, you know from your notes that a hydrogen bond is an attraction between a slightly positively charged hydrogen atom and a slightly negatively charged atom nearby, which is typically oxygen. And folks, I'm going to introduce the concept of hydrogen bonds to you in the concept of water. Okay, so if you look at page 35, figure 2.6, we in fact are seeing some of the relevant information. Okay, all right. So let's begin here, and I'm going to have some questions for you along the way. Okay, so I'm going to draw a water molecule, H2O. Okay, H2O. 2 atoms of hydrogen and an atom of oxygen. And I'm going to take these bonds and highlight them in a green rectangle. So I'm going to ask a question of somebody in the audience. Okay. Sarah Strebeck. Good morning, Sarah. Can you hear me?
Good morning, yes.
Good morning. So Sarah, I have a question for you. On your screen, I have these bonds that are highlighted with a green rectangle. Sarah, can you please tell me what type of bond these are?
Well, it wouldn't be hydrogen bonds, right?
Okay, thank you, Sarah. That's why I asked this question to see how folks are doing, because these are not hydrogen bonds. So think again, Sarah, what have we talked about very recently that would explain what kind of bonds these are?
Oh, would it be polar?
Completed. Yeah, say the whole thing.
Polar covalent bonds?
Okay, Sarah, you got it. Thank you so much. These are in fact polar covalent, right? They are not hydrogen bonds. They are polar covalent bonds from our conversation about 5 minutes ago, right? These are polar covalent bonds. So let me draw another water molecule to show you how hydrogen bonds come into existence. Okay, so another water molecule here, H2O. Okay, so these are also polar covalent bonds here, right? These are also polar covalent bonds here. Okay, so what I want you to notice is that the hydrogen bond is actually forming between the oxygen of the top water molecule and the hydrogen of the bottom water molecule. So I'm going to indicate that with a dotted dashed line here. Here we go. Okay, this is the hydrogen bond. Okay, now that might seem a little bit weird to you until you think about what you already know. Think about what you already know. What you already know is the following, that there is in fact going to be an unequal sharing of electrons. Okay, if we think about the top water molecule, there's going to be an unequal sharing of electrons between the top hydrogen and the top oxygen. That means that the hydrogen atom is going to become very slightly positively charged because most of its electrons spend most of their time around oxygen, which means oxygen takes on a slight negative charge. Okay, if you're wondering about that weird little symbol, okay, that means that's a Greek symbol which means partial. So that hydrogen has a partial positive and that oxygen has a partial negative. Same way over here. Partial positive, partial negative. This is going to happen on both water molecules. Okay. And because of this opposite of charge situation, right? Here we go. Let me outline it in orange. I'll try to do that. Okay, the top oxygen has a slight negative charge. The top hydrogen has a slight positive charge. And it's that opposite charges attract phenomenon we've talked about that actually is the hydrogen bond here. Okay. So first off, folks, let me ask you a question in the chat window. Okay. Please give me some feedback. Is the hydrogen bond between atoms of the same water molecule or between atoms of two different water molecules? What do you think, folks? What do you say? Okay, good. That's really the phenomenon. That's the point that I want you to get, right? Think about it. So far, we've talked about ionic bonds and covalent bonds, and those bonds were always between atoms that are part of the same molecule. But in this scenario with water, the hydrogen bond is between atoms that are part of two different water molecules. That's a huge difference, right? Think about that. Okay, so this is one of the unique properties of hydrogen bonds is that we often find them connecting atoms of two different molecules. Now, does it always have to be a bond between oxygen and hydrogen? No, sometimes it can be between nitrogen and hydrogen and other similar atoms, okay? But I think it suits our purposes very well at the beginning level here of the course to talk about hydrogen bonds in the context of water, okay? And we're going to go into a conversation about water in just a moment, okay? So I have another question for you. I want you to think about and give me some feedback in the chat window. One moment of time. It's going to take me a minute. Okay. Okay, here it comes. True or false? Hydrogen bonds can form when the atoms of each molecule are bound by nonpolar covalent bonds. True or false? What do you think, folks? Okay, I love that so many of you are saying false, okay? Hopefully, you're really processing this, and that's exactly what I want you to see, right? If in fact, the bonds that are highlighted by the green rectangles were nonpolar, if they were nonpolar, then that means the hydrogen and oxygens of a single water molecule would not have positive and negative charges. There'd be no polarity to those bonds whatsoever. And if that happened, there'd be no negative and positive to actually create the hydrogen bond between the water molecules. So well done, folks. That's exactly correct. And I'm going to take note of this in the drawing here. Note how hydrogen bonds form only when the bonds within each water molecule are polar covalent. If they were nonpolar covalent, you would not form hydrogen bonds. Okay, nicely done, folks. Nicely done. All right. So I don't want to beat a dead horse about this, but I'm just going to ask you, do you have any questions at this time? Okay, everybody's silent, so I'm going to assume that you are okay, and I'm going to keep going with some new content here, okay? So let me see here. I want to turn, see if I can, all right. Sometimes my electronic document doesn't work so good here. Okay, so let's keep on going. This is not what I want. Okay, I'm going to create a new document for right now. Okay, so chapter 2 continued. All right, folks, so we're done talking about chemical bonds. So if you've survived that, congratulations. Okay, these are forces of attractions that hold atoms together to build molecules, which then build larger structures, nanomachines, to build cells, to build tissues, to build organs, organ systems, and away we go. Okay. All right. Okay. All right. So think about it today. We have this winter wonderland outside, right? And part of the problem is that we have some ice on the road, okay? And so think about it. Townships and boroughs and municipalities have tow trucks out and they're putting salt down on the road. Think about why they're doing that. The presence of the salt is interacting with the water of the ice in some way. Why is that helpful to us to to provide better traction on the roads. Okay, why are they doing that? I'll leave that as an open question for now. Okay, so we need to talk about water, folks. I introduced water in the context of hydrogen bonds 3 minutes ago, right? We need to talk about the interesting and important properties of water. Okay, so let's state some facts about water, some things that you want to be aware of. First off, okay, so I'm basically on page 39, 40, 39 and 40, 39 and 40, okay? So why water is such a big deal is because our bodies are made of so much of it, okay? About 65 to 70% of the mass of each of your cells is simply due to the presence of water, okay? So roughly 65 to 70% of each cell's mass is water, okay? Think about that. If you weigh 100 pounds, then that means of that 100 pounds, roughly 65 pounds is simply that of water, okay? If you weigh 100 pounds, that means roughly 65 pounds of your body weight is just water, okay? People don't like to think of it this way, but you know, when we ask what is a human being, basically a human being is a big sack of water with 2 eyeballs, right? We are all big sacks of water with 2 eyeballs. Water is the environment that all the biochemical reactions that must take place happen. It is the environment that the biochemistry happens in so that it works correctly, right? Let me ask you a question in the chat window. Just give me an honest answer. Let me see if my technology will work. One moment. Have you given any conscious thought to the air in the room you're in today? Okay. I mean, let's be honest, some of you might have, because you might say, well, the temperature was cold, so I needed to turn on the heater, right? That kind of thing happens, okay? But what I'm suggesting to you is very frequently, do we not all, myself included, do we not take for granted that there's simply air present in the room we are in? We just take it for granted so we can breathe. We take it for granted. We assume it's going to be there so we don't give it any conscious thought. But my goodness, if something happened to draw the air out of the room we were in, wow, we would become violently aware and uncomfortable of that reality rapidly. That's how it is with water inside cells. Water is like the air. It's everywhere inside cells, and it provides the chemical background for other chemical reactions to do their work. Okay, so water is the background for all other important chemical reactions inside cells to happen, okay? Water is not just a background, it is actually a participant. It is actually a participant in the chemistry of our bodies. Okay, so just as an example here, okay, things you will read about if you haven't finished reading chapter 2, things you will read about and be asked to think about are involving water. So please turn to page 45, figure 215. Page 45, figure 215. Okay, and so let me give you an example. First, we have hydrolysis. Okay, hydrolysis is when water is used to break something down. So I have a question for you, and I'll put this question in your notes here. Looking at figure 215, I'll just ask it this way. In figure 215, is sucrose or glucose and fructose being broken down? Go ahead and give me some feedback in the chat window there. Is it sucrose or glucose and fructose that are being broken down? What do you say? Is it sucrose that's being broken down, or is it glucose plus fructose that's being broken down? Okay. You see, in fact, folks, that it's sucrose, right? If you look at sucrose on the right side of the page and you follow your eyes gently to the left, you see a chemical arrow which reads hydrolysis, meaning hydrolysis, the use of water to break things down. Sucrose is being broken down by hydrolysis in that chemical reaction of figure 215. Okay. All right. So that's an example of how water is used inside cells to allow the chemistry of the cell to take place. Right. Water is going to be used to break down the nutrients of the food that you ingest. At the same time, sometimes water is actually manufactured by processes that assemble things. Again, here we're going to be talking about dehydration synthesis. Dehydration synthesis is when molecules have atoms removed for the purposes of linking them together, and in the process of linking these molecules together, we pull off atoms that allow water to form. When water forms from atoms that are removed from other molecules that are being linked together. Okay, so think about it. In figure 215, glucose plus fructose are being linked together to form sucrose. And to do that, you notice your book goes out of the way to highlight the OH atoms on glucose and the hydrogen atom on fructose that are actually removed during that chemical step to build water. Okay? So again, we're talking about water. We're not talking too much about the chemistry here yet, but we're talking about water and telling you that water is a participant in all the chemical reactions of a cell, and we must never forget that. That's extremely important. Okay. All right. Any questions so far? All right, let's keep rolling. Number 4. Okay. So water is a fantastic solvent. Okay, what the heck does that mean? Well, that means, folks, that water is very good at dissolving things. Okay, and I could qualify that and say water is very good at dissolving most things. It's not very good at dissolving oil, is it? That doesn't work too good. Okay, but most things water is very good at dissolving. So you're going to want to become comfortable with the following statement. Okay, a solution equals a solvent plus a solute. Okay, and so if we define these things, a solution is the entire liquid with dissolved goodies in it. So let's define these things, right? Solvent is the portion of the solution that does the dissolving. Okay, it is usually the liquid that does the dissolving. Okay, and in cells, that liquid is always going to be water. It's never going to be another substance. It's not going to be antifreeze or alcohol. It's just not compatible with life, okay? Okay, this is always water inside cells. There's never an example of it being something else. A solute is the portion of the solution that is being dissolved. Okay, it is the portion of the solution that's being dissolved. We could say it is the solid material that is being dissolved. Okay, and so let's go with an example here. Let's see what we can do here. See if we can make some sense of this. Let's say that I have the following. Let's say that I have a cup of unsweetened coffee. Okay, maybe you're drinking coffee this morning. I don't know. So let's say we have a cup of unsweetened coffee. Doesn't really matter that it's in a cup, but think of a cup of coffee. And so the cup of coffee, let me ask you, a cup of coffee is going to be made of a solvent plus a solute. So my question is this, and please respond into the chat window. In our cup of coffee, what exactly is the solvent? What exactly is the solvent? Okay, Ryan, appreciate your participation. Robin and Jarrett, Lucy, good job. Okay, so let's not make this more complicated than it is. It is in fact water, right? You brew a pot of coffee using some water, do you not? So that's the solvent is in fact the water. And so my next question is, well, what exactly is the solute? In the cup of coffee, what is the solute? Okay, so Robin, I see you say coffee, and I think you're probably right. Let's maybe be just a little bit more precise. Coffee grounds, okay, very good, right? So in other words, why does the water that you use to brew the coffee, why does the water become a dark brownish black? It's because the water is dissolving the pigments from the coffee grinds to turn the water black. Exactly correct. Okay, so the solute is the coffee grinds, okay, all the molecules that make the coffee beans, okay? That is the solute, and that is what is dissolved in the water, okay? Another question. If you sweetened the cup of coffee with sugar, would sugar be additional solvent or additional solute? If you sweeten the cup of coffee with sugar, would sugar be additional solvent or additional solute? What do you think, folks? Okay, good job, Robin and Jarrett, Kiana, good job. Okay, so it would be additional solute, right? Additional solid material that is dissolved by the water of the coffee. Okay. All right, so I think you got it, folks. I think you got it. And it's really important that you appreciate that water is a good solvent. When you ingest food, when you eat, your body's going to digest it through processes that you will primarily learn about in AMP2. We're not going to talk about it in AMP1. But in AMP2, you're going to learn about it. And then those nutrients are going to be placed into your bloodstream. And your bloodstream is basically water, right? It's colored water. And that water will dissolve the nutrients, and your heart will contract and squeeze and push the blood throughout all the blood vessels of your body from your brain to your big toe. And it will distribute those dissolved solutes, those dissolved nutrients to your cells of your body, so your body maintains health and vigor. Okay, folks, do you have any questions right now? Okay, not hearing anything. Hopefully you're not passed out on your sofa. All right, very good. Let's continue. So, water is a fantastic solvent. Next, number 5. Water is a fantastic temperature buffer. Fantastic temperature buffer. This is a fancy way of saying that water is very, very good at resisting changes in temperature. Okay, so you might ask yourself, well, why does this matter? Why does this matter? Okay, folks, it matters because your body needs to stay at a consistent temperature to work properly, to have health. Okay. You know, it's always generally reported that the temperature of the body is 98.6. Well, folks, you know, that is the average temperature. The average healthy body temperature is about 98.6 degrees Fahrenheit plus or minus 1 degree Fahrenheit, right? So you could be 99.6 and still be normal. That's not a fever. You could be 97.6 and that's still considered normal. There's nothing unusual. And in fact, many folks run even a little bit lower without any problems, okay? But the point is, whatever your personal body temperature is, whatever your personal norm is for body temperature, your body wants to stay there because it works best when it's constant with temperature, okay? So why does this matter? Because your body works best when there's a constant body temperature. And you could certainly ask again, well, why? Why do I need a constant body temperature? Why do I need this? Okay. And so the question can be answered this way, and this is extremely important for beginning biology students, right? You are a beginner biology student. If you're in this course, you should know this. Okay. Changes in temperature have the ability to literally change the three-dimensional shape of molecules. Okay? Changes in temperature will change the 3D shape of molecules. Okay? So you might next state, well, who cares? Why does this matter? Okay? Well, again, there's a logic here, folks. I'm going to put a statement in your notes that is so important that if you have children, you should tattoo this statement onto their forehead. If you do not have children, you should tattoo it onto your forehead. Okay? Here it is. The three-dimensional shape of a molecule defines its function. The three-dimensional shape of a molecule defines its function. So mega important for beginning students to appreciate. And you know what? You all know this. You all know this, but you might not really appreciate that you know it. Think about this. Okay. Do you happen to have a door at your home that, based on what time of year it is, winter or summertime, that door becomes easier or harder to open and close? Because the wood of the door maybe expands in the summertime and it gets harder to get the darn thing to close properly in the door frame. Or in the wintertime, with less heat energy, the fabric of the wood actually contracts, gets a little bit more compact, and so it opens and closes easier. Do you have a door like this? Have you experienced a door like this? Okay, let me say it to you this way. Think about your car key. If you look at your car key and you look at the shape of the perimeter of the key, there's all these bumps and crevices in the car key. And if you put that into your car door lock, it'll open the car door and everybody's happy. However, if you gave your car key to someone and they smashed those little crevices and things with a hammer and changed the shape of your car key, you can appreciate that the car key would no longer work in your car door lock to open the car door lock. If you change the shape of your car key, it does not work anymore. If you change the shape of a molecule, it will change its function. Okay, so we want a consistent body temperature so that molecules maintain a consistent shape in order to do a consistent function. And if anything changes the temperature of the body, think about a fever, for example, then the shape of molecules will change and they will not work correctly anymore. Okay, so consider how bad you feel when you have a fever. Okay, consider that for a moment. All right. I don't know about you, but when I have just a little bit of a cold and some sniffles and a scratchy throat, I can function enough to go to work. But think about the last time you had a serious fever, whether it be associated with flu or whatever. Now, if your fever got up to 103, 104, I bet you didn't feel good. I bet you really didn't want to go to work or school. I bet you wanted to lie down and rest. There's a lot of aspects to what fever is and why it matters and how it's important. But in the context of our current conversation, when the brain decides that you have an infection that must be battled, right? There's a bacterium in you making you sick, or there's a coronavirus making you sick. The brain's thermostat is in the hypothalamus, and it tells the body to make changes to hold on to more heat energy and not release that heat energy. That results in your body temperature going up. When your body temperature goes up, the shape of molecules inside your cells changes. They don't work as effectively as they should, and you feel ill because of it. Now, your body's doing that because your body is also trying to change the shape of the molecules inside the microorganism that's actually making you sick. So if we can hold on to more heat energy and change the shape of the molecules inside the bacterium that's making you sick, then the bacterium can't work as well as it would normally, and we might end up killing the bacteria and killing the microbe that's making you ill. Okay, so there's sort of a Russian roulette or game of chicken philosophy that Mother Nature uses when combating pathogens. Okay, folks, am I making sense? Does that work for you? Any questions? Okay, I'm going to keep rolling here. All right, so water is a fantastic temperature buffer. It ensures that our body stays a consistent temperature, so our molecules stay a consistent shape, so they do a consistent job. Very, very important. Okay. Next, number six. Number six we can cover actually pretty darn quickly here, And that's simply to say something that I think you all appreciate. Water is a fantastic lubricant, and it's used as a lubricating liquid in many areas of the body. Water is a wonderful lubricant, okay? It is very good at reducing friction. Very good at reducing friction. And of course, if we reduce friction, we reduce the damage done to our organs, we reduce the damage done to our joints, right? Think about your shoulder joint, right? Think about your shoulder joint. Okay, I'm not going to spin my shoulder joint because I've got arthritis in it and it hurts, okay? But your shoulder joint is a synovial joint, which means there's a synovial cavity, which means there's synovial fluid. There's a liquid-based fluid in the shoulder. It's made of water, and it reduces friction between the bones that are articulating, between the head of the humerus and the glenoid cavity of the scapula, right, which you're learning about in lab right now. So water is a lubricant, reduces friction. It minimizes wear and tear on our body. Okay. All right, folks. Next major topic about water. Water influences the pH of a cell. Water influences the pH of a cell. Okay, I'll just say water influences pH. It does influence the pH of a cell. It also influences the pH of all body fluids, including blood plasma. Okay, so this is something we need to talk about. pH is a very important idea. And so pH is actually talked to you about on page 41 and 42, 41 and 42. So this opens up a can of worms. It opens up a can of worms because this is a very deep topic that we need to talk about. Okay, so there's some terms that we simply have to take time to define at this moment. Okay, so let's start with pH. pH stands for potential of hydrogen. Potential of hydrogen. And, you know, while that's nice, who cares? What the heck is it? What the heck is pH? Well, folks, pH is a scale. It is a scale. Just like a yardstick is sort of an object which represents a scale of length to measure things, how long something is, pH is a chemical scale used to measure the concentration of hydrogen ions in a solution. Okay. A scale used to measure the concentration of hydrogen ions in a solution. And the first thing that should come up is, well, why does this matter? Why does this matter, right? In our course, there's many times that you are going to have to memorize facts, things that we know to be true, right? The humerus is the upper bone of your arm, right? It is above your elbow. That's a fact. But many times you got to stop and ask, well, okay, now that I know this fact, why does it matter? Who cares? What's the big deal here? Why is this important? Why should we spend time talking about it? And here's why it's a big deal. Okay, cells move hydrogen ions around so that your cells will use hydrogen ions as sort of a chemical dollar bill. And what I mean by that is hydrogen ions can be attached to molecules, or hydrogen atoms can be pulled off from molecules and turned into hydrogen ions. And when you add a hydrogen ion or pull off a hydrogen atom that becomes a hydrogen ion, you change the shape of a molecule. So the big deal is similar to temperature. If you change temperature, you change the shape of a molecule. If you change the hydrogen ion concentration of a liquid, you will ultimately change the shape of the molecules dissolved in that liquid, which will change their function, how well they do their job, okay? The concentration, let me put it this way, the availability of hydrogen ions in a solution alters the shape of molecules dissolved in that solution. And of course, if we change the shape of a molecule, we will change its function. Okay? So the availability of hydrogen ions does lead to a change in the shape of molecules in that environment. We change their shape, we change their function. That's why pH is a big, big deal. Okay? And I will try to show you in just a little bit, you know, kind of roughly how that works, because it may not be obvious to you at this moment how that really works. Okay? So just bear with me. All right. So when we talk about pH, we have to talk about acids and bases, right? Because the hydrogen ion concentration helps determine whether we define a solution as acidic or basic, okay? So an acid is any molecule that releases hydrogen atoms that turn into hydrogen ions when placed in water, okay? An alternative way of thinking about this is an acid is any molecule that increases the hydrogen ion concentration of a solution, okay? So there's a couple things here that keep coming up, okay? And the first is this word concentration. What is concentration, right? We talked about concentration up here in pH. We're talking about it down here with an acid. So what the heck do I mean by concentration? Okay, the challenging part of your course at this moment is that you're studying words potentially for the first time or for the first time in a very long time of being in school. And these words, when you look at their definition, the definition uses additional words that you don't understand, right? If you read that pH is a scale used to measure the concentration of hydrogen ions, you might not know what a hydrogen ion is, you may not know what concentration is, and in such cases, you are obligated to look these things up, right? Otherwise, it's never going to make sense. So folks, concentration is a really deep topic that physicists and chemists talk about a lot. I don't want to get into the depth of the topic because it kind of takes us on a wild goose chase we don't need right now. But let me say it to you this way. Concentration for our purposes and for getting you started should be thought of as a mass of material. Okay, a mass of material dissolved in a volume of liquid. A mass of material dissolved in a volume of liquid. Or alternatively, a quantity of solute dissolved in a volume of solvent. You think about what we just learned a little bit ago about these terms. A quantity of solute, a mass dissolved in a volume of solvent. So, let me ask a question in the chat window. Okay, question in the chat window. All right. Here it comes. If each of you swallows 1 tablet of baby aspirin containing 81 milligrams of aspirin, will each of you have the same concentration of aspirin in your bloodstream? I mean, you're all taking the same amount of the drug, so it would seem logical you'd have the same concentration, right? No. Okay, right? The answer is no, because obviously you are all different shapes and sizes, which means you all have different volumes of blood plasma, right? You know, or you will come to know through this course, that the average blood plasma volume for an adult male is 5 to 6 liters of blood. The average blood plasma volume for an average woman is 4 to 5 liters, okay? So, an example of concentration could be 81 milligrams of aspirin dissolved in 5 liters of blood plasma. That would be a statement of concentration. And you do need to think about that, okay? You appreciate that concentration is such a majorly important topic in the clinical setting, right? If an anesthesiologist does not get the concentration of anesthesia correct in your bloodstream during surgery, there can be significant consequences, right? If the concentration of anesthesia is too low, you're going to wake up in the middle of surgery and probably not be too happy about that. At the same time, if the concentration of anesthesia in your blood is too high during surgery, you may never wake up. And obviously, you're not going to be happy about that either, okay? So the idea of concentration is so very important in clinical medicine. Okay, let's keep going. Any questions so far? All right, so let me try to give you a little bit of an understanding about what I mean by an acid, because it's one thing to say it and define it, but it's still something that you don't always get by just reading the definition, okay? And I'll emphasize, you notice in the definition for acid, I say that an acid is any molecule that releases hydrogen atoms that turn into hydrogen ions when placed in water. An acid as a molecule is meaningless. It has no meaning unless it's in water. If it's not in water, it's not really an acid anymore. It's just a molecule. An acid only has meaning in terms of its relationship with water. That's it. Okay? So as an example, okay, let me do this. Okay, and I think I'm going to combine some ideas right now. Remember, we said that pH is important because if we change the pH of the environment, we will change the shape of the molecules in it. Remember that. So let's start with this. Let's say I have HCl, which is hydrochloric acid. Let's say I have water. And let's say I have hemoglobin, which you know is the compound in your red blood cells responsible for transporting oxygen to your tissues. Now, hemoglobin has a big chemical structure. I don't have it memorized, folks. That's why we have books. And you will learn about the structure of hemoglobin in AMP2. All right, so suffice it to say, hemoglobin is a molecule that ultimately has a negative charge on its surface. So I'm drawing hemoglobin with a minus sign there. What's going to happen to this acid in the presence of water is that the acid will separate into ions. So we're going to have an H plus a Cl minus plus water plus hemoglobin. Okay, stay with me, folks. We need to finish this topic before we close off today. Okay, and so I have more to do here, but let me ask you a question before I change gears here. Okay, so on the left side of the chemical equation that I'm bracketing with a green bracket, on the left side, type into the chat window the answer to the following question. Hold on. There we go. On the left side of the chemical reaction, indicated with the green bracket, how many hydrogen ions are there? What do you say, folks? How many hydrogen ions are there? Okay. I'm seeing some of you say 0, but I'm also seeing others giving me a higher number, 2 and so forth. So how about the rest of you? There's a lot of people that are not answering. Everybody should be answering. Okay. All right. So the answer is 0. And if you understand why it's 0, that's really good. But I suspect some of you might be just going along for the ride because that happens a lot. There are, in fact, 0 hydrogen ions because a hydrogen ion is an H plus, right? And on that side of the chemical reaction, there are no H pluses. But on the opposite side, the right side of the chemical reaction, by the other green bracket, you can see there are, in fact, there is one hydrogen ion, and it's right here. Right? So that should be consistent with our chemical definition of an acid as any molecule that increases the hydrogen ion concentration of a solution. We've gone from 0 to 1. Okay. I'm going to continue, folks, maybe 2 minutes here. Okay. So are you okay with that idea that I've just shown to you? Everybody okay? All right, so let's get back to another topic here. This idea of, well, hydrogen ions can change the shape of molecules, and that's exactly correct. Okay, what you'll notice here is there's a positively charged hydrogen ion and a negatively charged hemoglobin. So it is very possible that this hydrogen ion will come over here and attach to the negatively charged hemoglobin. And I'll just draw this out differently now. And so in the next moment of time, the chemical reaction would become this. Cl minus plus water plus hemoglobin with a hydrogen atom attached. And what I'm trying to point out to you is the following. The hemoglobin with the minus charge and the hemoglobin with the hydrogen atom, they might seem like they are the same thing, but they are not. They are not the same thing. They are similar things, but similar is not identical. And what I'm trying to get you to see is that these two forms of hemoglobin have different shapes. And folks, in the chat window, please make your instructor feel nice and good today. In the chat window, if these two forms of hemoglobin have different shapes, should we expect them to have the same or different function? Same or different function? Give me a response in the chat window. Okay, good. Good. Thank you so much. I feel much better now. Thank you. Okay, they have different function. Okay. All right. So we are definitely over time, so I'm going to stop, folks. Do you have any questions? Okay, I'm going to momentarily pause the recording.
This meeting is being recorded.
Okay, welcome back, everyone. So this is the first day where you had a homework assignment to do, lab exercises 1 and 2. And so we will go over several of the homework assignments this morning together. And so before I start, I wanted to point out to you, and please give me a moment, I've got to let someone else into the room here. Just a moment. Okay, I wanted to point out to you that your own lab manual does contain the answers to some of the work that you were assigned. If you turn to page 699, you will see the answer key back there, right? So for example, exercise 1, figure 1.1. And so you were assigned some work from exercise 1 today, and you were assigned some of the before going to lab activities. Okay, and on page 2 of your lab manual, the first thing it says was label figure 1.1. Well, on the back, page 699, there you have the answers, okay? So my point is that some of the material that you are assigned, you can check for yourself to see if you got it right. And that kind of content, I don't want to spend lab time on reviewing it because you can check yourself, and I would encourage you to do that. Now, there are portions of the lab homework that are not answered at the back of the lab manual, specifically the reviewing your knowledge and using your knowledge portions of the homework. And for that, we need to go over that together, you and I together, so that we can make sure everybody's understanding things, okay? So let's begin our review today on page 7 of your lab manual, reviewing your knowledge, letter A, body regions. And I don't like to sit here and just read things to you because that gets tedious for me and it gets boring for you. So what I want to do is I will go around the virtual room and call on each of you to contribute five or so answers from the homework, okay? So I'm going to be asking all of you to do that. When I call your name, please simply unmute your microphone and tell us the answers that you thought were correct for the assignment, okay? This is a very friendly place. It is okay if you get something wrong. That's okay. Don't worry about it, okay? All right, so page 7, letter A is the body regions. I'm just going to go around the virtual room here. So Robin, can you please give us your answers for questions 1 through 5 on page 7?
Number 1 is femoral. Number 2 is brachial. Number 3 is antebrachial. Number 4, crural. And number 5, thoracic.
Okay, thank you, Robin. I appreciate that. And so, folks, let me say, Robin is not wrong, but she did misinterpret the language of the question, right? And Robin, what you did is something that many students do. If we read the instructions, it says, identify the body regions using common terms. So rather than,
Okay.
So for number 1, I would expect.
I have that as well.
Okay. Do you want to give that to me?
I have those as well. Thigh. So you're saying thigh, arm, forearm, leg, and chest.
Beautiful. That's exactly what we want for that question. You got it. Okay, good job. So I'll repeat that for the benefit of everyone. Thank you, Robin. Number 1 is thigh. Number 2, arm. 3, forearm. 4, leg, and 5, chest. Okay, Toyin.
I'm sorry, what page is it? I forgot.
Okay, Melinda, we're on page 7 of your lab manual. Letter A, the body regions.
Okay, thanks.
Okay. All right. Toyin, please give us 6 through 10. Toyin, I'm not hearing you. Are you having a problem with your microphone? Okay. All right, Toyin, if you're having a technology issue, don't worry about it. We'll come back to you, okay? All right. Okay, so Joe, can you give us 6 through 10?
Numbers. So I did the same thing with the using the anatomical terms instead of the common, but let's try this. Between the diaphragm and hip bones would be the midsection or stomach, maybe. Area of the trunk inferior to the hip bones would be the pelvis. Posterior trunk that is located between the neck and the buttocks would be your back. Curved area where upper limb attaches to upper border trunk would be shoulder. And area on anterior surface where lower limb attaches to pelvis would be groin.
Okay, Joe, you did a nice job there on the fly, so thank you for that. Let me suggest for number 6, maybe abdomen would be a nice term for that. Okay, so 6 abdomen, 7 pelvis, 8 back, 9 shoulder, and 10 groin. Okay, Lucy Horse. Lucy, please give us 11 through 15.
I also didn't use the common terms, but I can try as best as I can. For 11, would it be the buttocks? 12, the armpit. 13, the fore or the arm. 14, the leg. 15, the knee. Is that correct?
No, it is not, but you got some of them right, Lucy. Okay, so thank you for trying. Let me go over those. Number 11 would be buttocks. 12 is armpit. 13 is forearm. 14 would be thigh. And 15 would be, wow. Oh, 15 would be groin. 15 would be groin. Okay. Ryan Ditterline. Ryan, could you give us 16 through 20, please?
Sure. 16, I have wrist. 17, I have knee. 18, hip. 19, true. And 20, true.
Okay, that was fine, Ryan. Thank you so much. Again, 16 wrist, 17 knee, 18 hip, 19 and 20 are true. Before I continue, folks, do you need anything from page 7 repeated? Okay, let's turn to page 8. Here you folks can use your anatomical terms, right? I know you want to do it. I can see it. It's just bubbling out of you, right? You just want the anatomical terms. Okay. All right. So Emmanuel, can you give us 1 through 5?
1 is umbilicus, 2 is thoracic, 3 is octic, 4 is palmar, 5 is acromial.
Okay, nice job, Emmanuel. Again, number 1, umbilicus, 2, thoracic, 3, otic, 4, palmar, 5, acromial. All right, Lexus Ross. Lexus, please give us 6 through 10.
Antecubital, septic, nasal, cervical, popliteal.
Okay, thank you, Lexus. Lexus, your speech was very silent. I could barely hear you. So I'm just going to repeat those again. Number 6, antecubital, 7, facial, 8, nasal, 9, cervical, and 10, popliteal. Okay, Kiana Branch. Kiana, can you give us 11 through 15?
Yeah, I have 11 as carpal, anti-brachial, dorsal, anticubical, and oral.
Okay, thank you, Kiana. Pretty good. I would change your answer to 14 to axilla, but let me go over all of those. Number 10, popliteal. 11, carpus. 12, antebrachial. 13, dorsum. 14, axilla. And 15, oral. Jada Rivera. Jada, can you please give us 16 through 20?
I'm not gonna lie, I think I did the wrong thing. Because
Oh.
I'm not finding any of the answers are mine are wrong.
Okay, Jada.
Okay.
Jada, if you need help interpreting what it was you were supposed to do, please stick around after lab today and I can help you, okay?
Okay.
All right. So let me go over those. 16 would be patellar, 17 sternum, 18 coxal, 19 is fibular. Now there is an alternative term for that region, which is perineal. So you could have had fibular or perineal for 19, and 20 is sural. Okay. Amber Prince, can you please give us 21 through 25?
Yeah. Okay. So 21 is brachial, 22 is digital, 23 is manual, 24 is mammary, and 25 is buckle.
Okay, that is correct, Amber. Thank you very much. Once again, 21 brachial, 22 digital, 23 manual, 24 mammary, and 25 buckle. Lindsay Tate. Lindsay, can you give us 26 through 30, please?
26 is calcaneal, 27 is plantar, 28 is inguinal, 29 is cephalic, and 30 is mental.
Okay, nicely done, Lindsay. That was fine. Once again, 26 calcaneal, 27 plantar, 28 inguinal, 29 cephalic, and 30 mental. Mackenzie Patterson. Okay, Mackenzie, could you please give us 31 through 35?
Yep. The pedal, the orbital, pubic, femoral, and then 35. Wouldn't that be would that be cranial too or facial? Because I got confused on that one.
Yep, it is cranial. Your
Okay.
first instinct was right.
Okay.
Okay, so thank you. Once again, 31 is pedal, 32 orbital, 33 pubic, 34 femoral, 35 cranial. Okay, Jarrett, can you give us 36 through 40?
For 36, I got frontal, 37 vertebral, 38 occipital, 39 crural, and 40 I got lumbar.
Okay, nicely done, Jarrett. No problems. 36 is frontal, 37 vertebral, 38 occipital, 39 crural, C-R-U-R-A-L, and 40 is pelvic. Okay, let me see here. Melinda, I saw your comment to me in the chat window. So again, if if there's any confusion on your part as to what you are to do, please ask me, okay? All right, so Sarah Strebick. Sarah, can you give us 41 through 45?
Yes. For 41, I got pelvic, 42 scapular, 43 cranial, 44 brachial, and 45, I said pectoral / thoracic. I
Okay,
wasn't sure which one.
all right. Sarah, in the case of 45, you could use either term and be good with that. Okay, so 41 is pelvic, 42 scapular, 43 olecranal, 44 brachium, 45 thoracic or pectoral. Folks, do you need any part of letter B, 1 through 45, repeated?
Question for 22. Could it also be phalangeal?
Yes, yes,
Okay.
it could be. And thank you for bringing that up. Sometimes, Lucy, there are alternative answers that would be acceptable, okay? Other questions? Okay, all right. Let's see, there's two folks that haven't had a chance to go yet, so I'm going to continue down this route and then I will pick up the pace a little bit for us. Page 9, letter C at the bottom, body planes and sections. Marche, can you please give us 1 through 5? Marche, Marche, do you hear me? Marche, are you there?
Could you check the chat box?
Okay, I understand, Marche. And again, please get with me if there's something that you're not understanding. Okay, Elisa Diaz. Elisa, can you give us 1 through 5? Elisa, I'm not hearing you. Are you okay, Elisa? Okay, it would seem that maybe we're having some technical issues here. So I will give the answers out, okay? Number 1 would be parasagittal. Number 2 is a frontal plane, which is also called a coronal plane. Number 3 is a transverse plane. Number 4 is mid-sagittal. Number 5, you could probably answer different ways and be correct. So as example, 2 planes that would satisfy this question would be frontal and transverse. But if we leave a little bit of flexibility in our interpretation, I think we could also be correct with mid-sagittal and even potentially oblique, although that would be a little strange. Okay. All right. And then let me finish letter D on page 10. Letter D on page 10. Number 1, superior. 2, lateral. 3, proximal. 4, medial. 5, distal. 6, ipsilateral. 7, inferior. 8, anterior. 9, posterior. 10, contralateral. So folks, let me ask you, are there any parts of letters C or D you would like me to repeat? All right. All right. It looks like everybody is. Yeah. I'm seeing a few comments in the chat window, and I do appreciate that. You know, if there's something that you really want me to focus on, I'd ask you to please speak up a little bit. Don't be shy about unmuting your microphone. Okay, so Toyin, letter D. Letter D, number 3 is proximal. Number 5 is distal. Number 6 is ipsilateral. I-P-S-I-L-A-T-E-R-A-L, ipsilateral. Okay. Anything else, folks? Okay, let's go to using your knowledge on page 11. Okay, so this is a little bit hard to do since I do not have an electronic version of this image that I can share with you, but we can just, we'll do our best to describe this. So number 1 here, a 55-year-old male presented with an irregularly shaped and abnormally pigmented mole in the left scapular region. So where you would draw your dot on the pictures below, the best place would be on the letter B, posterior view. Identify the left shoulder blade region and put a dot there, right? If you think about your own body, it would be here, right? If you can see me in the chat window or in the video window, it would be back here. That's where you would have placed your dot. Number 2, 37-year-old woman goes to the emergency room with a 3rd degree on the right brachial region, just proximal to the antecubital region. So for that one, on letter A, on the woman's right arm, right, which is always diagonally opposite your right arm. On the woman's right arm, where your elbow is, go up just about an inch. Go up an inch or 2 and put a dot right there. That's where your dot should be. Number 3, 19-year-old female identified by a tattoo on the fibular surface of the right leg. Fibular surface on the right leg, just proximal to the tarsal region, indicate below. Well, you could have done this on either picture, but I'll tell you for the anterior view. On the anterior view, you would have placed a dot on that woman's right leg, down by her ankle, on the side of the ankle that's towards her tiny little toe, not the big toe, but exactly opposite from the big toe is where you would have placed your dot. Okay, all right. Any questions about those 3 images? Okay. Continuing. Questions at the bottom of page 11 and the top of page 12. Number 4 would be distal. 5 would be anterior. 6 would be superior. 7 would be medial. Letter B has some interesting photographs here, some interesting pictures. Okay, number 8 is a reflection of picture A. That is a frontal section. Picture A is a frontal section. Number 9, the sagittal section is picture C as in Charlie. C as in Charlie. And number 10 is the final one, which is letter B, image B as in boy. So 8 is A, 9 is C, 10 is B. Okay, any questions? All right, let's go on to lab exercise 2. All right, pages 21 and 22. 21 and 22 for reviewing your knowledge. Here we go. Letter A on page 21. functions and identification of organ systems. Number 1 is respiratory. 2 is nervous. 3 is muscular. 4 is integumentary. 5, cardiovascular. 6 is digestive. 7 is urinary. 8 is endocrine. 9 is skeletal. 10 is reproductive. 11 is both lymphatic and immune, because those are two sides of the same coin, lymphatic and immune. Letter B, organ system identification. Number 1 is lymphatic. 2 is digestive. 3 is respiratory. 4 is cardiovascular. 5 is integumentary. 6 is urinary. 7 is reproductive. 8 is endocrine. 9 is nervous. 10 is reproductive and endocrine. 11 is reproductive. 12 is digestive. 13 is digestive and endocrine. 14 and 15 are both endocrine. 14 and 15 are endocrine. So let me just pause and ask you, do you need any of letter A or letter B repeated? Okay, moving on. Letter C, body cavities on page 22. Number 1 is C for cranial. 2 is A for abdominal and PT for peritoneal. 3 is T for thoracic and PC for pericardial. 4 is T for thoracic and PL for pleural. 5 is thoracic. 6 is A for abdominal and PT for peritoneal. 7 is V for vertebral. 8 is A for abdominal and PT for peritoneal. 9 is A for abdominal. 8 is A for abdominal and PT for peritoneal. 9 is A for abdominal. 10, 11, and 12 are all P for pelvic. P for pelvic for 10, 11, and 12. Okay, and then the letter D, abdominopelvic quadrants and regions. Number 1 is the right upper quadrant and the right hypochondriac region. Number 2 is the left upper quadrant and the epigastric region. Number 3 is the left upper quadrant and the left hypochondriac region. Number 4 is the right upper quadrant. And then for the region, you could say either the right hypochondriac or the epigastric, because sometimes the gallbladder kind of goes between those two depending on how your personal anatomy is situated. Number 5 is the right lower quadrant and the right inguinal region. 6 is the left upper quadrant and the left lumbar region. 7 is the right lower quadrant and the right inguinal region. 8 is the right lower quadrant and the left lower quadrant. Okay, both of those, right lower and left lower quadrants, and the hypogastric region. And then if we finish out page 22, we have the serous membranes. Okay, Number 1 is the parietal pericardium. 2 is the visceral pleura. 3 is the visceral peritoneum. 4 is the serous fluid. Okay, I mentioned that water is a good lubricating fluid. Serous fluid is made of water. And then number 5 asks you to circle the organs that are found within the peritoneal cavity. I have noticed over the years that if you look at different textbooks as to what is in the peritoneal cavity, you sometimes get inconsistent and different answers. And so to keep things simple, I will suggest the answers from your own lab manual. Okay, so I would have expected that you circled pancreas, kidneys, the adrenal glands, part of the large intestine, the small intestine, the aorta, and the inferior vena cava, Okay, so I know that was a lot of stuff there. So let me ask you anything from pages 21 or 22 that you would like me to repeat. Okay, not hearing anything, not seeing anything in it. Excuse me, in the chat window. I'll continue. Okay, using your knowledge, page 23 for lab exercises 2. Okay, letter A, homeostatic imbalances of organ systems. Okay, for muscular dystrophy, that is definitely the muscular system. We're going to be talking about that later in the course, folks, but muscular dystrophy is a big deal. And unfortunately, I mean, you know, you don't wish a disease on anybody, but it almost exclusively attacks males because of its genetic relationship. At any rate, muscular dystrophy is a problem with the dystrophin protein, which is encoded by the dystrophin gene. There's been over 50 medically documented mutations in that gene that can really wreak havoc with people. So number 1 is the muscular system. Number 2, hypothyroidism would be the endocrine system. 3, for myocardial ischemia, that would be the cardiovascular system. 4, infectious mononucleosis, well, obviously the lymphatic and immune systems are the major players there. Letter B, body cavities and the serous membranes. Number 5 is T for thoracic and PC for pericardial. Number 6, we have our famous gallbladder removal, A for abdominal and PT for peritoneal. Number 7 is a spinal tap, pretty serious procedure. That would be V for vertebral. Letter C, abdominopelvic quadrants. The answer to 8 is letter B, as in boy, which is appendix. Number 9, the answer is also letter B or ovary. Letter B or ovary. Then we have some pretty pictures for you on page 24. Hopefully you enjoyed this. Even if you don't get them all right, it's kind of neat to see this and start to learn, you know, what's inside your body. All right, number 10. 10 is the brain. Number 11 is your spinal cord. Number 12 is the right lung, Number 13 is your heart. 13 is your heart. 14 is the diaphragm, right? The diaphragm is a flat muscle that separates the thoracic and abdominal cavities. 15 is the liver. 15 is liver. 16 is your stomach. 17 is the left kidney. 18 is the right kidney. Number 19 is the urinary bladder, where you store your urine. Number 20 is the left ureter. The ureter is the tube that connects the kidney to the bladder. So when your kidney manufactures the urine, the pee trickles down into the bladder for storage until you're ready to use the bathroom. Okay. All right, folks, do you have any questions on pages 23 or 24 that need repeated? Okay, so I'm seeing in the chat window number 20. Okay, number 20 is the left ureter. Number 10 is the brain. Number 11 is the spinal cord. Okay, anything else? Okay. All right, folks. So congratulations. You made it through your very first homework assignment. Okay. Let me encourage you. It really is very important that you do the work. Yes, it can be a lot of work, a lot of effort. It can be tedious and frustrating at times, but it truly is in your best interest to do it. Okay. If you're thinking and getting much of the questions right, then you should feel confident that the course is going to go more smoothly for you. All right, so next week, you have 2 homework assignments, lab exercises 8 and 9 that are due. Okay. All right, so since we're done talking about the homework answers, I'm now going to stop the recording. And I will be sending a link to the recording to everybody later today. For those that are not with us, you now have the answers to your homework, and let me know how I can help you. Okay, so I'm going to pause. I'm going to stop the recording.